Continuation from our last class, organic chemistry. The next homologous series we are looking into are alkanols, which are also called alcohols, and they have the general form. An hydroxy group is attached to an alkyl group, and this particular one is called a monohydric alkanol. From our previous lessons, I believe we should have the idea about dihydric, trihydric, or we can call them polyhydric alkanol if we have more than one hydroxyl. So the functional group is this OH, which is responsible for the chemical properties of alkanol. The simplest form of alkanols is methanol, which is also called wood spirit. So methanol obviously has only one carbon. So alkyl group with one carbon is CH3. So it means methanol is CH3 OH. The next member with two carbon is ethanol. For ethanol, the alkyl group is what? Ethyl, which is C2H5OH. And you can guess the next one should be propanol. So for monohydric alkanol, we can generalize, and all of this represent the alkyl group. Methanol is called wood spirit because it is gotten from destructive distillation of wood. And the most important alkanol is the ethanol, normally referred to as alcohol. Before we look into ethanol, the most important alkanol, let's quickly talk about the primary, secondary, and tertiary alkanol. I've explained that earlier during naming. Then also dihydric, monohydric, and trihydric alkanol. If a single alkyl group is attached, it is a primary alkanol. But if you have two alkyl groups, it is what? Secondary. And if it has three alkyl groups attached to the carbon carrying the OH, it is tertiary. So the alkyl group may be the same or different. So primary, secondary, tertiary. Let's give an example. Sorry, go and watch the first video on organic chemistry. My first video, example 14 under naming. The first one is 2-methyl propanol. Second one is butan-2-ol. Third one is 2-methyl propan-2-ol. They are all. The first one is primary, followed by secondary and tertiary. Look into that. That is example 14, 15, 16. Then example 17 and 18. The first one is dihydric, and 18 is what? Trihydric. So the first one is ethane-1,2-diol, which is ethylene glycol, which I even made mention in the second video. So go and check, go at the first video. Number 18 example under naming is what? Propan-1,2,3-triol. That's glycerol. Now I think we cannot go to ethanol, but I advise you write those examples. This is primary, secondary, tertiary, dihydric, trihydric. Watch the first video and write this down before we move to ethanol. So ethanol is C2H5OH, and we can also write as what? CH3CH2OH. So this is ethanol, or you can draw it and it will look like this. Whether you write it this way, you write it this way, or write this way, it's the same thing. And for the molecular formula, we count all the carbons. We have two carbons, C2. We have 6 hydrogen, H6, and we have one oxygen, O. But there are other families or homologous series that can also have the same molecular formula. Now, how can we prepare alcohol or ethanol? There are many ways of doing this. Let's look into some. The first one is from ethene. Ethanol can be prepared from ethene. How? We can do this by hydration of ethene using steam, and we get ethanol. OH. But we need H2SO4 as catalyst, and this will happen under extremely high temperature and high pressure. Temperature of about 600 degrees Celsius and pressure about 80 to 100 atm. And the second one is by fermentation. So what is fermentation? Right. Fermentation is a slow decomposition by microorganisms of large organic molecules, such as starch, into smaller molecules, such as ethanol. So starch are large organic molecules, and they can be broken down into what? Smaller molecules, like ethanol that you want in this case, by what we call microorganisms, yeast. So this microorganism can be gotten from yeast and other sources. Now let's explain this process. But please write down the meaning of fermentation as I stated earlier. Now, from starchy foods like rice, guinea corn, maize, or millet, we can extract starch. These starch are treated with malt at about 60 degrees Celsius for about 2 hours or 1 hour, and it partially contains what we call enzyme diastase. So this enzyme is important. In this case, it's an organic catalyst. So this particular enzymes, through the action of this enzyme, we are going to form maltose. So if you have 2 water molecules here, we form 2 molecules of maltose. The more water molecule we have, the more maltose we have here. So this maltose now, in the presence of enzyme maltase, then this maltose will be converted to ethanol, and CO2 is going to be evolved. After this process to this maltose, we need to add yeast at room temperature. So this maltase will first convert this maltose to glucose first, but in the presence of water here. So the yeast contains maltase and zymase. So the maltase will first convert the maltose to glucose. Now this glucose will now be converted to ethanol and CO2 by the presence of zymase. Hence, we have our final product, ethanol. Let me summarize that. From starchy food, we extract starch, then treat it with malt, which contains enzyme diastase. So that converts starch to N-maltose. So we have N starch, it's a giant molecule. Then this maltose is now treated with yeast. Yeast contains maltase and zymase. So the maltase will convert the maltose to glucose. Then the zymase from the yeast will now convert the glucose to ethanol, and this CO2 is going to be given out. Then at the end we have ethanol. We can also get ethanol from sucrose. So from sucrose, in the presence of the enzyme invertase, so sucrose can be converted to glucose and fructose. And this glucose and fructose, they are isomers. So we call them isomeric sugars. So it's either from starch we get maltose, and from maltose, with the presence of maltase, we get glucose. This glucose, zymase, will now allow it to turn towards ethanol. Or directly from sucrose, using invertase, we get glucose straight and fructose. So this glucose can now be acted upon by enzyme zymase, so that glucose will move out So after this, the next step is to write this one below. So I don't need to repeat that. But there's a little problem here. The ethanol gotten from fermentation, they have low concentration. So meaning if you have let's say 100 volume, let's say 100 cm cube or 100 meter cube of ethanol from this process, about 80% is water, or about 80% is not ethanol. So it has only about 18% purity. So we can use fractional distillation in order to get the ethanol. So ethanol with very high concentration are called rectified spirits. Why those ones that are almost 100% are called absolute ethanol, and they are very hygroscopic. So if they are exposed to atmosphere, they absorb moisture. So in order for them to remain anhydrous, they must be kept away from the atmosphere. Now let's talk about the physical property of ethanol. So right, please. Number 1, ethanol are colorless, volatile liquid with a characteristic taste and smell. So they have a special taste and smell that they are known with. They are colorless, but they are highly volatile. If they are exposed to air, they can easily escape. Number 2, they readily dissolve in water. So they have high solubility because of the presence of OH minus. They have no action on litmus paper, and they have boiling point about 80 degrees Celsius, 78 degrees Celsius to be precise. Boiling point of 78 degrees Celsius. So methanol and ethanol, they are similar in property, just that methanol has lower boiling point of about 67 degrees Celsius. So generally, most hydrocarbons or organic compounds or molecules, they are not soluble in water. But for Alkanol, because of the hydroxy group, so that what made them water soluble. But the more the number of carbon atoms increases, so their solubility also decreases. For example, all these primary Alkanol that with more than 5 carbons, they tend to be insoluble. So this can be understood using the concept of dipole. Now let's talk about its chemical properties. Chemical properties of alkanols. Ethanol to be precise. First, let's talk about combustion. Similar to hydrocarbon, we are getting water and CO2. Reaction with alkali metals such as sodium and potassium. So reaction with sodium will give us what? Sodium ethanoate, and hydrogen gas is going to be given out. Sorry, not sodium ethanoate, sodium ethoxide. Next, reaction with chloride such as phosphorus chloride. So ethanol reacts vigorously with this particular phosphorus oxide in the code, so liberating steamy fumes of hydrogen chloride and also chloroethane. Now let's talk about oxidation. So in the presence of potassium heptaoxodichromate, that should be dichromate 14 minus 2, 12, that's 6. So ethanol will be oxidized to give us what? Ethanal. So that's alkanol. From alkanol to alkanal. Then further oxidation in the presence of H2SO4, now this is still there, will now give us what? Carboxylic acid. So meaning from ethanol, we can go to ethanal by oxidation. From ethanol, we can move to what? Alkanoic by what? Further oxidation, but in the presence of H2SO4. The next one is esterification. And this esterification is like it's like a neutralization process, acid base giving salt and water. So in this case, ethanol, it can act as a base, because it has OH. Then if you have acid such as ethanoic, ethanoic can act as an acid. That's why they are called carboxylic acid. So we are going to get a particular salt called ester and water, not actually salt. So when alkanol reacts with acid, we get ester, and water is going to produce in this. We can call this organic neutralization. That's just made up name, but not. For example, here we have alkanol and alkanoic. So this is ethanol and ethanoic to give us. So this is what? Ethyl ethanoate. So alkanoates are esters. So it is as though. So from here we can have C3 CH3 COO minus H plus, and then we have what? C2H5 plus, then OH minus. So by the extra radical, this and this come together to give this water. Why this one as negative positive come to the back of this? So it was C3Cu, then C2H5. C3Cu, C2H5. So this process is called what? Esterification. We are still going to talk about it later. The next is dehydration. Indirectly, I've explained dehydration during the preparation of ethene, whereby we use the dehydration of what? Ethanol. So this reaction is familiar. You can go and check preparation of ethene. And recall, if the ethanol is in excess, then we are going to form ethoxyethane. So instead of dehydrating this to give us this, so we can add more ethanol to this in excess, they are going to have this. That is what? Ethoxyethane. Just note, if we dehydrate alcohol or ethanol, we are going to get ethene. But if the ethanol is in excess, we are going to get what? Ethoxyethane. So these are the chemical properties of alkanol. Now let's talk about the uses. What are the uses of ethanol? Number one, so they are used as solvents to dissolve resins or soaps or perfume dyes. So they are used as what? Organic solvents. Two, they are raw material to manufacture new substances such as ethanol, esters, allies, ethoxyethane, and other forms. So like example of this one, we have ethoxyethane here. We have what? Esterification to produce esters and the likes. Also ethanol, where is it here? So to produce ethanol and carboxylic acid too. So it can be used to produce other chemicals. They also use as fuel in racing cars and in rockets also, but not ordinarily. They have to mix it with petrol or to have a particular octane rating. Now another thing about ethanol, they have very low freezing point. Because of this low freezing point, they are usually used as what? Antifreeze agent in automobile radiators. And lastly, I don't know if you should call this advantage, we also use ethanol in alcoholic beverages such as beers, wines, and the likes. Although scientifically, I don't think that's an advantage, because even little amount of alcohol is poisonous to the body as time goes by. So this is the end of alkanol. So the next is going to be alkanoic acid carboxylic group or carboxylic acid. They have the general form, which can also be written as RCOOH. So go back to the first lecture. from example 19 to example 22 under naming. So we have ethene-dioic acid, we have 6 butene-dioic and 2,3-dihydroxyl butene-dioic acid. We also have 2-hydroxypropan 1,2,3 tricarboxylic acid. So even benzoic acid and the likes. So they are all carboxylic acid. Please go and check the first lecture, example 19 to 24. They are all carboxylic group. So no, these carboxylic acids sometimes are also called fatty acids, and the simplest form is methanoic acid. We have HCOOH. This methanoic, followed by ethanoic, followed by propanoic, butanoic, and the likes. So this methanoic is also known as formic acid, and this ethanoic is also called acetic acid. This is just propanoic acid. So they all differ by CH2, and that's from the definition of homologous series. And when this carboxylic acid, they can always dissociate. For example, let's take ethanol for example. So this ethanol can dissociate to give CH3COO minus plus H plus. So it means it is a polar molecule, or polar molecule. So because it's polar, there's going to be a polar bond or dipole bond between their molecules, and that is why they have higher boiling points compared to the size of their molecules, because of what? Their dipole. The most important part of this alkanoic is actually ethanoic. So how can ethanoic be produced? They can be prepared by complete oxidation of ethanol. Go and check the last chemical property of ethanol, dehydration, that we just did now. So if you understand, if you see, at the end of the day, we form what? Ethanoic acid from ethanol. So that's complete oxidation of what? Ethanol. Go and check that and write it here. Then we have another way. We can do that by boiling methyl cyanide with an acid. Methyl cyanide with acid is here. Let's add more water molecules. So this is what we have at the end of the day. So we have our ethanol, and lastly, so we can go to sodium ethanoate. So if you have this anhydrous sodium ethanoate, then we distill it with H2SO4. So this will give us, this Na will be replaced and one H will come here. So you have CH3COOH. Then what happen? This one will drop by one, that will be HSO4 with sodium, that's sodium hydrogen and acidic salt. So we have our ethanol. Now let's talk about its physical properties. First, it is acidic in nature. That is why it turns blue, transparent, and it dilutes from aspartate just like an acid. So it has a boiling point of 118 degrees Celsius, slightly just above water, and freezes into ice-like structure below 17 degrees Celsius. That's why sometimes it is called glacier ethanoic acid. You know, when you talk about glacier, talk about those giant ice at the poles. They are very solid water. Why? Because they are polar solvents. They are polar in nature, and they are colorless liquid, but with sharp and pungent smell. They have a characteristic sharp and pungent smell that you know that this is actually ethanoic acid. What about its chemical properties? So we are first going to talk about its acidic properties. Now, its acidic property has already been described here. It is monobasic. So it is going to act like monobasic acids. So, and it's going to have the same chemical property as other acid. So it is an organic acid. It is monobasic, and is a weak acid. So it carries out with carbonate to what? Liberate CO2. It carries out with metals to liberate H2 gas. It can undergo neutralization by producing salt and water when it writes alkali. That's neutralization. Second is ester formation. Recall, part of the chemical property of alkanol is they react with alkanoic to give what? Esters. So if you reverse it, same thing goes for here. So when alkanoic reacts with alkanol, they form what? Esters, and water is also given out. Or simply water is produced. So the ethyl form here, the ester form here is what? Ethyl ethanoate. So, and this reaction is actually reversible. You know, we can go forward. The forward reaction is called esterification, and we can also go backward. That backward is the hydrolysis of esters to give back carboxylic acid and alcohol. Next is reaction with chlorine. And this will give 2-chloroethanoic acid and HCl. But a catalyst is needed here. And that catalyst is sunlight or iodine. So, and similar to the substitution reaction for alkanes. So this is what it has one chlorine. So this monochloro, you can call it monochloroethanoic acid. You can have dichloro. You can even have tetrachloro. So if all the hydrogen here are replaced, then we can have CCl3. So the end product is what? Trichloroethanoic acid. Number 4. So what happens if it undergoes reduction in the presence of a reducing agent? When ethanoic acid is reduced appropriately, it's going to give us what? Ethanol. From ethanoic acid to ethanol. The reducing agent used in this case is what? Lithium tetrahydroaluminate. So this will supply 4 hydrogen to this, and it introduce what? Ethanol, and water will be produced. And the 5th use will be what called decarboxylation. So in this, we are going to capitalize on the acidic property. When ethanoic reacts with this carbonate, we are going to form this one, sodium ethanoate. So this sodium ethanoate will be needed. So first, we remove H, although it still look like carboxylic group because of this COO. Then, if we recall methane, how methane is produced in the laboratory, it is heated in equal proportion with sodium hydroxide from soda lime. And the reason we use sodium and soda lime, not this sodium hydroxide, is because this NaOH can attack the glass easily. And sodium hydroxide is very deliquescent. So that, and we need to use anhydrous chitricuna. Let me call it that way. So at the end of the day, methane will be produced. Therefore, the sodium, we are going to have sodium oxide, and also CO2 is going to be involved. So 2 gases will be formed in this case. So what happens at the end of the day, we will not have about this carboxylic group at all. So that's what we call it decarboxylation. To serve as a revision, let me quickly draw the setup for the preparation of methane from what? Sodium ethanoate salt. So here you have anhydrous sodium ethanoate. So this is heated up strongly, then the steam is produced, then we are having what? These 2 gases coming here. So, and it's going to collect it over water. So this setup for the production of methane. So the first is to get this from this reaction. Then this is mixed with soda lime, NaOH from soda lime. Then in this setup, then we have methane collected over water, and we have CH4. It is collected over water because it is not soluble in water. In case you are asked why it's passed through water, the response is that water is used to cool the gas, because the gas has very high temperature. So water is used to cool the gas, and also to remove soluble impurities. For example, CO2, and also some NaOH odd form can still be trapped inside. So, and this will allow us to get methane, or methane can be collected downward by downward displacement of water, since it is insoluble in water. So major reason is to cool down the methane, and also to remove some impurity and allow downward displacement of water. Now let's talk about its uses. What are the uses of ethanoic acid? Number 1, it is mainly used to produce various chemicals such as propanone or acetone, and also various dyes. They are also used in aspirin to also produce what we call ethynyl ethanoate, or call it the vinyl acetate. And these are used to produce some resins known as the vinyl resins. They are also used to prepare what we call to manufacture synthetic fibers like rayon and artificial silk in all their important solvents. They are also used in food industry for preservation of what? Flavoring food. And lastly, they are used to in the coagulation of rubber latex. And lastly, they are used in the production of esters through the process called esterification. Under Alkanol, I mentioned esterification. Under Alkanoic, I also mentioned esterification. So it's important for us to even discuss about esters themselves. In a way, it's as though we are moving to the next family, which is what? Alkanoic. They have the general form. And these esters, they are the primary constituent of naturally occurring fats and oils. And something peculiar about esters, please note, is that they have pleasant smell, and they are largely responsible for the fragrance of flowers and the flavors of fruits. For example, banana oil, they are gotten from pentyl ethanoate. Pentyl is C5H11. So ethanoate will be, so this pentyl ethanoate, and it has the smell of banana, while octyl ethanoate has the smell of oranges. So octyl means you have 8 times 16 minus 115. So smell of bananas, smell of oranges. Now the question is, how can we prepare this in the laboratory? Note, for these two alkyl group, one of them is from the acid, meaning carboxylic acid, while the other one is from the alkanol. This is the definition of esterification. So if I have ethanoic acid and ethanol, the ester form will be what? Ethyl ethanoate. How? Look at this. So here, take this H and take this OH. So then you attach this C2H5 to the back of what? CO. So at the end we having CH3, CO, OH gone, then this C2H5 comes to meet it. So HA and OH here forms water. So this is what? Ethyl 2-carbon ethanoate. So if you want to get the smell of orange, ester that will smell like orange, so it means you are going to use ethanoic acid, but what? We are not going to use what? Octanol. So what happens? We take this OH away, take this H away, then bring this one to the back of this. So we having. So now is it. So this is now what? Octyl ethanoate, which will smell like orange. Okay, let's pick one. Let's just pick this ethyl ethanoate. How do you produce this in the laboratory, and what are its physical and chemical properties? You can either write it this way, or you can also write as CH3CO, CH2, CH3, or you can draw the structure. Alright, so produce this ethyl ethanoate. First is we mix equal volume of concentrated sulfuric acid and ethanol. We shake them and we add drops slowly of ethanol and ethanoic glacial ethanoic acid. So this drop is added, and this through this oil bath. So this is heated up to about 150 degrees Celsius, and what happens at that temperature? We'll see ethyl ethanoate being distilled out. So it come out as vapor. So cold water is poured there just to cool it down. Then we have about ethyl ethanoate here, although with some impurities. What are the impurities? Now, because ethanol is in excess, we have ethanol here, we also have it here. So upon we have some ethanol that are unreacted. So in that case, it's like the ethanoic acid is the limiting reagent. So we use necessary separation techniques to remove all these 4 impurities. So at the end of the day, we are left with pure ethyl ethanoate. So now let's move to the physical properties. They are volatile and colorless liquid with pleasant smell. So they are slightly soluble in water. So they are dissolved in non-polar solvents such as benzene, ethanol, or ethoxyethane. And 3, they have a boiling point of 75 degrees Celsius. They are pure form has a boiling point of 75, but with impurities it will be higher than that. Chemical property number 1, they can undergo hydrolysis, the opposite of esterification. So meaning ethyl ethanoate can react with water to give back ethanoic acid and ethanol. Although this is a very slow process, but in the presence of what? Acid or base. So in alkaline medium or in acidic medium, it can proceed faster. Secondly, if alkali is used, you get the salt of the alkali instead of the acid. So we having CH3COONA in this case plus ethanol. If ammonia is bubbled through the solution containing ethyl ethanoate, we are going to form ethanol and ethanamine. So this is ethanamine. We've done this under naming first video. And lastly, ethyl ethanoate can be reduced. It can undergo reduction to give us ethanol. it to be reduced not by removal of oxygen but addition of what? Hydrogen from the reducing agent. Then what are the uses? Number one, they are used mainly as solvent for cellulose nitrate, paint, nail varnishes, and common adhesives. So the mixtures of esters can be formed or can be used to produce what we call thinner water. Because of their sweet smell, they are used in perfumes, cosmetics, and flavoring for foods. I think we can end it here for esters. Before we move to the next family, recall I said at the start of what esters that they are the main constituent of fat and oils. So now let's talk about fat and oils. Okay, let's move to fat and oils. Fat and oils belong to a general group called lipids. While fats are from animal origins, oils are from plants, but they are all esters. We just did esters, but these esters are formed from what we call trihydric alkanol, which is glycerol. So this is propan 1, 2, 3 triol. That's the 18th compound we named in the first video. And this glycerol is esterified with 3 molecules of fatty acids. So these fatty acids are actually from, and one of their sources is from lipids. So 3 molecules. So this is the first one. So 3 molecules, and the alkyl group can be same or they can be different. So what will be the products? So this H and this OH will come and form water molecule. Then this RCOO minus will come into this alkyl group. So we are going to form 3 water molecules. They will form an ester. So let's bring this RCOO, remove this one and replace it for H. Now you see this fatty acid, all this alkyl group, they have large number of carbon. They can have number of carbon up to like even 18. So C18, that's 36 minus 1, 35. H35. So which can be linked to COOH. So this fatty acid from lipid. Now, most importantly, this fatty acid, they are categorized into 2. We have the saturated and the unsaturated fatty acid. Similar to saturated hydrocarbon, so the hydrocarbon in the fatty acid, if they are all single bond, it's saturated. But if the hydrocarbon in the fatty acid, from this alkyl group, if they have at least 1 double bond, they are what? Unsaturated. So fats are formed from saturated fatty acid and they have higher boiling point. So while oils are formed from unsaturated fatty acid and they have lower boiling point. And oils from plants can be converted into fats. And this process is what we call the hydrogenation of oil. What is hydrogenation? Addition of hydrogen. So since it is unsaturated, it has at least 1 double bond. So if hydrogen is added, that double bond will be split into single bonds, and it becomes fat. Margarine is produced through this process, in case you ask. In the process of this hydrogenation of oil, 3 things are essential. First, the catalyst. We use finely divided nickel, and this happens at the temperature of about 180 degrees Celsius and a pressure of 5 atm. So this fat formed are also called the hardened oil. So this hardened oil cannot be transformed to margarine by adding some other substances such as salt, vitamins, and skimmed milk, and eventually we get margarine. So we've explained what we mean by hydrogenation, and also what we call hydrolysis of oil, and there are 2 different things. I've explained hydrogenation of oil and how margarine is formed. Now let's talk about hydrolysis of oil, which is a concept called saponification, formation of soap. Notice that these esters here are what we refer to as fat and oil. This fatty acid with glycerol giving us fat and oil, they are all esters. So if you take this ester now, then we hydrolyze it using caustic soda. Now what do you think will happen? We are going to use 3 molecules. Let's make it this way. So what will be the product? So all these cations here, sodium ion, will replace all this alkyl group. So all this will break off and they form this. Then here you have 3 OH, each will attach to the alkyl group. What is this? Glycerol, propan 1,2,3-triol. And what are these? These are all called soap. So this process is called saponification, hydrolysis of fat and oil. So these are the main constituents of soap, although that's not all about soap. So in case if you ask what is saponification, what's the answer? So you can simply say saponification is the alkaline hydrolysis of fat or oils to produce soap and glycerol. So another name for this is what we call it what? Triglyceride. Glyceride. This reaction is slow unless the temperature is increased to about 80 to 100 degrees Celsius. Before we talk about the uses of fat and oil, let's give examples of saturated and unsaturated fatty acids. So we have palmitic acid from palm oil and stearic acid from animal fat. And from peanut oil and olive oil, we have what called the oleic acid. And from vegetable oil, we have what called the linoleic acid. Saturated fatty acid, unsaturated fatty acid. Now let's talk about the uses of fat and oil. Uses. Number 1, they are mainly used as food. Yes, fats are consumed as food. And they can be added and turned to margarine also. Number 3, some of them are used to make soap. We use palm oil for cooking, and we also use coconut oil for making soap. They will call a particular oil the linseed, which are used in production of paint, linseed. Now, how do you test for fat and oil? So we have to test the paper test and the Sudan 3 test. If oil or melted fats are on top of what? Filter paper, so a translucent grease spot will be formed, meaning it's either fat or oil, or it indicates the presence of fat or oil, melted fat. Then for the Sudan 3 test, so we can add few drops of water to that oil, then we shake it, then we add few drops of Sudan 3. So if the mixture is stained red, so it indicates that what we have there is fat and oil, or fat or oil. Now, soaps are generally solid. So we also have what called soap powders and liquid form of what? Soap. And in general, they are called detergents. So anything that can clean surfaces, they are called detergent. And detergent are of 2 kinds. So they are either soapy or soapless. Any substance that has the ability to clean objects are called detergents, and they are either soapy or soapless. And soap can either be solid form, in powder, or in liquid form. Now let's quickly talk about soapy and soapless detergents, then we can move to the next family, alkanals and alkanones, aldehydes and ketones. So these detergents are either soapy detergents or soapless detergents. And soapy detergents, they are sodium salt of fatty acid, as I've explained. And there are 2 kinds. We have the hard soap laundry. We have the hard soap and the soft soap. So for the hard soap, they are using laundry to wash clothes, plates, and the likes. But for the soft soap, they are using what? In toilets to wash hands, to bathe and the likes. So now, for the hard soap, they are sodium salt of saturated acid, which I give an example. We are coming back to that. For the soft soap, so they are potassium salt of unsaturated fatty acid. And if you recall, this is general formula. So we have this ester, and recall I told you, this alkyl group, they have large number of carbon atoms. And this is gotten by the reaction between fatty acid and ethanol, if you recall. So the type of saturated fatty acid we use here is the stearic acid that we can get from animal fat. Then what next? Saponification. What is saponification? We hydrolyze this ester with caustic soda, 3 molecules. And what will the products? The soap and glycerol. So I've explained this before. Now, what is the alkyl group used in this case? Our R. And I told this R, they can be the same or different. So the alkyl group we use here is carbon with 17 atoms. C17, 7 times 34 plus 1, that is what? 35. H35. So if you have that with this, let's replace this R. And let's suppose they are all the same. So let's replace this with this and see what we get. So let's hydrolyze it to 3 molecules of caustic soda. Then let them exchange ion. And the product will be, so every sodium atom will replace the whole of this. Sorry, every OH will replace the whole of this. So this whole will be to what? Sodium. Then we are going to have, so I'm going to have 3 of this. So this sodium takes this. So we are going to have this in 3 places. Then this structure, so for every CH2, OH will attach to form glycerol. So this is a sodium salt of saturated acid. So this is minus, this is plus. So this is a salt. Sorry, this is soap, yeah. It's a kind of salt, sodium salt. Now, how many carbons do we have here? 70 plus 1, 18 carbons. So how do you name this one? Sodium, 18 is what? Octa is 8, then deca is 10. So 18 is going to octadecanate. So we can just call it called sodium octadecanate salt. So to get a salt soap, we are going to use what? KOH instead. Then we are going to use what? Unsaturated what? Acid with Alkanol to get, you know, the ester or the oil or fat. Now, what is now the nature of this soap? So not only this particular soap, in general, for soapy detergent, what is their nature? First, know that each of these salts, they have a long hydrocarbon chain. Then we talk about ionic head. These are called the ionic head. The long chain, the ionic head. It is Na plus for hard soap. For soft soap, it's going to be what? K plus. So this ionic head is hydrophilic. Why this one we call it the tail? It is what? Hydrophobic. So soap in general, they have dual nature. So when you say hydrophobic, from the word phobic, something that doesn't have to relate with water, something that doesn't dissolve in water. So this part is not soluble in water, but it's soluble in what? Organic solvent like oil and the likes. So this one, because of their what? You know, poles, dipoles, they are polar. So it is hydrophilic. It can dissolve in what? In water. Or let's say it is soluble in water. So some part is insoluble in water, so why some part is what? Soluble in water. So it has a dual nature. So if they ask you what is the nature of soap, the nature of soap, it has a dual nature, the hydrophobic tail and the hydrophilic head. So this is the hydrocarbon, you know, we can also call it the hydrocarbon what? Tail, and this is the head. So suppose this is the water layer. So when soap are added, we have this structure. Why this? Because water is a polar solvent. So the head is hydrophilic, so it will go attach to water. While the other end is hydrophobic, so it tries to move away from the water, like being scared of water. If this soap is dissolved in water, so if they are pushed down in water and mixed together, so this each molecule of the soap, they will reorientate themselves to form what we call the myceles, something like this. The head will point outward and the tail will point inward to form a spherical structure called the mycelium. So with this, we can explain the cleansing action of soap. So what actually happens is, if we have oil and water mixed together, oil and water, it will form immiscible liquids. But if we shake it vigorously, what happens is that the oil will form droplets around the water or within the water. Suppose this water and we pour oil in it and shake it in a beaker, so you have something like this. So the oil droplet will move around. So if we now pour soap inside, pour soap inside and we mix it together, so all these myceles will surround each droplet of oil. So these myceles surround each droplet of oil to prevent the coagulation of this droplet with a bigger one. So in this case, all these myceles, they act as what we call emulsifying agent. So the soap in this case, they act as an emulsifying agent. And this happens because the tail, they will dissolve in the oil. Because, you know, the tail are non-polar, they will dissolve in the oil. But for the heads, they have ions. So there'll be a kind of electrostatic repulsion, between the heads and the water, preventing coalescing or coagulation, called emulsifying process. The heads will surround and the tails project inward. We have something like this. Suppose you have a fabric, and this fabric has oil stains. So what happens? We'll make soap inside water, then this fabric will put inside this mixture. Then what are you going to have? So the tails will dissolve in the oil, and the head will dissolve in what? In water. As the water attracts the heads, water has H2O. So this will attract this, while this will attract this. So as the water attracts the head, so what happens is that the stain spots will move upward. And this will enable more soap particles to dissolve in the what? Stain. So when you scrub the clothes, so when you scrub the fabric, so the stain parts, whether it's oil, whether it's grease, will emulsify. And by the time you rinse with ordinary water, what happens? All the oily part or grease part goes away. Then you have a clean fabric. In short, the cleansing action of soap is due to what? The emulsifying of what? Of oil in water by the action of the hydrophilic head and the hydrophobic tail. But the thing is, this particular soap we are talking about can only work very well if the water is soft. We have hard water and we have soft water. Because in hard water, it will form scums and it will lower the cleansing action. So if you have hard water, the first thing you have to do before you can use soap is to soften it. Then another disadvantage is that it is this is an advantage. It is biodegradable, so it can easily decompose. It can be decomposed by bacteria, and it will turn the soap into a simple organic compound. Simple inorganic compounds. So it doesn't cause water pollution. Unlike soapless detergents, they are non-biodegradable, so they cause water pollution. Just that we can use soapless detergents when the water is hard. So it will not reduce the cleansing action if we use soapless detergent. Although this soapless detergent, they have many applications. They have many applications over the soapy detergent. So, but the only thing is that from their structure, they are actually made from alkyl benzene sulfonate, and these are abbreviated as ABS. They are abbreviated as ABS. So benzene compound, they are aromatic, so they form cyclic, so they are not straight chains. So but currently detergents are now manufactured with straight chain hydrocarbons, so which are biodegradable. So briefly on the structure of soapless detergent, they also have their hydrophobic tail and hydrophilic head, and this tail are either long chain hydrocarbon, about 12 to 18 carbon atoms, or the tail can be benzene ring with a long alkyl group attached to the benzene, something like this. So this is the ring structure of benzene, and we have an alkyl group attached to it which has a long chain. So this is the tail, and this is the head, and they have very high solubility. Their solubility is very high because of the nature of their head. And in fact, sometimes even the head can be neutral for soapless detergent. And sometimes they are referred to as synthetic detergent, mainly because their raw materials are petrochemicals from refined crude oil. So I think that's all about detergents, soap, saponification, hydrogenation of and the likes. Now, before moving to the next family, which are aldehydes and ketones, so there is a general problem about soap and detergents. So when you say soap, note, if you say soap only, we are referring to soapy detergents. And when we say only detergent, most times we are referring to soapless detergents. Whether soapy or soapless, for commercial use, they usually contain some other substances, such as perfumes, brighteners, dyes, and antiseptics. And all these things, they contain phosphate ions, which are good fertilizers. So because of this, they cause algae in waterways. So, and if this they normally multiply beyond control. So, and this brings about water pollution. So because they will clog the waterways. Except if you want to use normal soap without all those antiseptics, but they're also important in order to avoid some kind of infection. So let's move to aldehydes and ketones very brief before talking about carbohydrates in detail.